Welcome to the Foundry by Forge College. In today's explainer, Designing Measurements for Latency Optimization, we're taking a massive leap forward. This is all part of our broader module on the performance analysis of Turbine protocol, sitting right inside the Exploring Turbine Data Transfer on Solana course, which, as you probably know by now, is a core piece of our Advanced Solana Concepts track. Now, if you caught our last explainer, Performance Evaluation Foundations for Turbine, you already know the basics. We talked about percentiles, network tracing, and how Turbine shreds data into smaller pieces so it can fly across the network in parallel. But today we're moving from the chalkboard straight to the workbench. We're going to take those foundational theories and build a rigorous, actual measurement lab for the Turbine protocol. Right off the bat, we run into the million-dollar question: how do we actually measure turbine speed without all the random system noise getting in the way? You see, we know all about P50s and network tracing conceptually, but when you are dealing with alive, breathing systems, there is always interference. If we just run a quick test and stare at a stopwatch, how on earth do we know we're measuring turbine's true speed, rather than just capturing a random network hiccup? Well, to solve that, here is our game plan for today, laid out in this crisp, patent-style blueprint. We're going to hit 1. Setting up the lab, 2. Controlling the variables, 3. Metrics that matter, 4. Core measurement parameters, 5. Building the baseline script, and 6. Real-world diagnostics. Let's get right into it.
Part 1. Setting up the lab and moving from theory to practice.
Okay, I want you to imagine literally putting on a white lab coat right now, because the golden rule here is to treat every single measurement run as an experiment trial in a highly controlled lab setting. We are totally stepping out of the theoretical phase. No more guessing, no more estimating. We are now acting as systematic engineers writing an actual baseline script. And look, a lab isn't a chaotic, messy room, right? It's pristine. Your measurement environment needs to be exactly the same way.
That brings us perfectly to part 2, controlling the variables, which is the absolute golden rule of testing. The core methodology we're using here is called controlled variation. Simply put, it means changing exactly one independent variable at a time while holding everything else perfectly constant to record your dependent observations. Without this level of rigor, any changes you see in speed could literally just be clock drift or random network jitter masquerading as turbine segmentation working its magic. We absolutely have to isolate those variables.
And I really cannot stress this enough. 1. You change exactly one independent variable at a time, period. If you're going to change the payload size, you have to keep the concurrency the same. If you start twisting multiple dials at once and the system suddenly gets faster, well, you have absolutely zero idea which tweak actually caused the result. Essentially, we're fighting a battle here. On one side, we have our independent and dependent variables, the things we actively control and measure, like payload size and concurrency. On the other side, the enemies of good data, nuisance variables. Think of nuisance variables like having a really messy roommate who decides to turn on the microwave right when you're trying to measure your Wi-Fi speed. It's going to completely scramble your data. We have to filter that noise out. Moving on to part 3, metrics that matter. It's time to look beyond the average. Here, we are comparing the typical experience, which is our median or P50 latency, against the absolute worst-case scenario, also known as tail latency, or our P95 and P99 metrics. Now, the median is great. It tells us the normal, sunny day experience of the network. But honestly, the P95 and P99 tails tell us how often transfers are getting stuck in the mud. That is exactly where users feel the pain, and that's where we need to focus our optimization. To really debug those nasty tail latencies, you've got to track per segment timings. We want to measure the time spent waiting in the queue, the actual transmission time, and the assembly time over at the receiver. By measuring exactly how long one of those little orange turbine shards spends in each specific phase, we can link the protocol's behavior directly to the end-to-end latency. It's kind of like tracking a package at every single sorting facility along its route, rather than just noting when it left the warehouse and when it hit your porch. Which leads us to part 4. Core measurement parameters. Let's set those dials. Take a look at this elegantly simple layout. For exact baseline values, we test payload sizes ranging from just 1 kilobyte all the way up to a full megabyte. For concurrency, testing 1, 4, or 16 parallel transfers is going to reveal exactly how queuing impacts the system. Then, running 10 to 30 repetitions ensures we have enough data to easily filter out those statistical outliers we talked about. And finally, we give the whole system an inter-run cooldown of about 5 to 30 seconds. This is crucial. It lets the caches and network buffers totally stabilize before we hammer it again. Part 5. Building the baseline script.
Here is our experiment sequence. This is the exact sequence to fire up our testing accelerator. Step 1, set a random seed, ensuring our payload content is completely deterministic. Step 2, start up your concurrency workers. Step 3, perform the transfer and record the precise start and end timestamps. Step 4, emit a JSON line with your data and trigger that cooldown phase. Notice how we're keeping the actual transfer operation abstracted in this script? That's so we can seamlessly swap in a turbine command later on without having to rewrite the whole loop. When we emit that data, this is the exact schema we use. We grab the run ID, transfer ID, start and end timestamps, payload size, concurrency, and node ID. Why this specific format? Because this compact JSON structure is perfectly machine parsable, which makes grouping and aggregating all that metadata later completely painless. Seriously, you do not want to be manually formatting spreadsheets. You want your scripts doing the heavy lifting for you. But hey, massive trap alert here. You must use synchronized clocks, record your time sync method, and include monotonically increasing sequence IDs. Remember, the reproducibility of your entire experiment relies on accurate timekeeping. If the clock on your sending node is even slightly out of sync with your receiving node, your latency math is going to be total garbage. So, ensure your clocks are perfectly synced, or at the very least, rely strictly on clear round-trip deltas. And finally, part 6, real-world diagnostics. How do we actually interpret these results? Okay, here is a super crucial diagnostic rule to live by. You might run a test and see that parallel transmission is clearing the network faster. You're thinking, awesome, everything is great. But if you look closer at the segment timings, you might discover you're actually just bottlenecking the assembly stage at the receiver. The data arrived incredibly fast, sure, but the receiver is choking on putting the turbine puzzle back together because it's basically trying to drink from a fire hose. Don't just blindly change the shard size, tune your assembly buffers instead. To make sure your diagnosis is actually correct, you need to collect environmental metadata too. We're talking CPU utilization, network interface counters, process queue length, and packet drop counters. Always check for system-level noise like NIC interrupts so you don't accidentally blame the turbine protocol for what is actually a host-level network drop. And by the way, as you explore other topics with us at Forge College, you'll see this theme pop up all the time. Verify the environment before you blame the protocol. Let's wrap this up and look at how it all stocks together. We started with Step 1, Performance Foundations, back in the last explainer. Today, Step 2, we build our rigorous baseline script inside a clean, controlled lab environment. And that sets the stage perfectly for Step 3, our upcoming throughput benchmarks. That baseline script you just designed, that's the exact measurement primitive we're going to use when we scale this whole thing up. So I'll leave you with this provocative thought. Is your baseline script running cleanly enough right now to serve as the control set for massive throughput scaling? Make sure your testing artifacts exits cleanly with 0 errors. Double-check those timestamps and fiercely protect your clean lab environment because we are about to put it under some serious load. Be sure to visit forge.college to dive into more Web3-related explainers before we crank up the scale in the next module. Thanks so much for joining me, and keep on building.